Hello and welcome everyone to this already fifth episode of our series of Atlas YouTube live talks. My name is Sascha Mehlhase. I'm a physicist at the Atlas experiment at CERN. For today's talk, we'll collect questions as usual in the YouTube live chat. So if you have any questions for today's speaker, then put them in the live talk. We'll pick them up after the talk in a question and answer session that follows, and we'll discuss that, and then the speaker will have a chance to hopefully address all of your questions. So now I'm happy to present Dr. Anne Sickles from University of Illinois at Urbana-Champaign as today's speaker. She's also a physicist in the Atlas collaboration, and before that was also at the PHENIX experiment at the Relativistic Heavy Ion Collider at Brookhaven National Lab in the United States. And then in Atlas, she was, amongst other things, the convener of the heavy ion group, physics analysis group inside Atlas, which also brings us to today's topic of her talk and to Anne herself, how to explore the quark-gluon plasma.
Okay, so thanks a lot. Let me share my slides. All right. So I think you should be able to see that. Is that correct? I hope. Yes.
Yeah.
Okay, so I'm going to tell you a little bit about the quark-gluon plasma, what it is, why we're interested in it, and how we actually study it. So hopefully you'll know a little bit more about this at the end of this talk. So it's very, very hot. And I think that's really the first question I want to address is how hot. There's a lot of different things that are hot in your life. And so how hot is the quark-gluon plasma? Let's set the scale for this. So here in Illinois, it's actually a pretty nice day. And it's about 80 degrees Fahrenheit here, 25 degrees Celsius for people in Europe. This is a nice day. That's hot. Well, lava is a lot hotter, right? Molten rock, that's a lot hotter, brings it at about 1,000 degrees Celsius. Okay, so that's pretty hot. You should definitely avoid swimming in lava or something. The sun, all right, everyone is familiar with the sun. It makes the earth hot. Obviously, it's a lot hotter than the earth. It's about 15 million degrees Celsius in the core of the sun, the center of the sun, which is a giant fusion reactor. So that's pretty stinking hot. The hottest thing that you can really observe around you, if you have the right tools, is the center of a supernova. So that is about 100 billion degrees Celsius. These numbers are getting a little more rough because they rely more on modeling. But that's the hottest thing that's happening right now in the universe. The quark-gluon plasma is quite a bit hotter. So it comes in at several trillion degrees. Now it doesn't matter Fahrenheit or Celsius. It's still really in the trillions. And we don't have a picture of this. So I'm going to tell you about what it is and how we study it. So in order to do that, I have to go back and I have to tell you a little bit about nature as we see it. So the atom is what's all around you. Everything you see is made up of atoms. So these have a very dense core, which is the nucleus of an atom. And everything around that is mostly empty. There's electrons there, but basically it's mostly empty. And so this is a nice image from Wikipedia that's just the gray shows you about all the electrons that are around, but they just zip around in an orbit around this very, very, very tiny core. And it's about at the scale of a few femtometers. So what is that? That's 10 to the minus 15 meters across. This is where the center of an atom is. So we're going to take a look at the nucleus. So this is my nice PowerPoint cartoon of the nucleus. 99% of the matter that you see around you, 99% of the mass of atoms, normal matter is in the nucleus. The nucleus varies in size from a hydrogen, which is a single proton in most cases, to uranium, which you've heard about, to the transuranic elements, which are even bigger. Okay, so this is just a bunch of circles. There's red and blue circles, and that is supposed to illustrate that the nucleus is composed of really two components, protons and neutrons. And for our purposes, we're not going to really worry about the difference between them. Protons have an electric charge and neutrons don't. So what holds all these protons and neutrons together? Well, that's the strong force. Physicists are not always the most creative when it comes to names. The strong force, it's very strong. It holds the nucleus together. And it's so much so that for the most of your life, you don't have to really worry about how it works or anything like that. You can go through your life totally oblivious to it. If you go through your life totally oblivious to one of the other fundamental forces like gravity, you will find yourself injured very quickly, right? So there are 4 fundamental forces: the strong force, gravity, the electromagnetic force, which gives you chemistry, biology, your iPhone, everything like that, and then the weak force, which I'm not going to mention. So the strong force is characterized by extremely strong interactions and an extremely short range of its validity, or interactions. Okay, so then we're going to have to look at what's inside the proton. So now we're going inside the proton and really the neutron too. Okay, so this is a picture. Some of you might have heard that the proton is made up of 3 quarks. So these are the constituents of the proton. They carry charge, electric charge. They also carry the charge of the strong force. They carry the quantum numbers of the proton, so they're what make a proton a proton. So the proton has 2 up quarks and a down quark. The neutron has 2 down quarks and an up quark, and this is what characterizes a proton, what makes it a proton. But if you look, this is a quantum system, and for those of you who haven't heard about quantum mechanics, don't worry. For those of you who have, I think you realize that word just implies an additional layer of complication. So what there are quark-antiquark pairs. So not only is there a quark, there's an antiquark, which is antimatter of the quark. And then there's this other particle, which is called the gluons. And the gluons, thankfully, they keep the quarks and gluons bound together inside the proton. And this is what provides the glue that keeps the proton together. And it also provides the glue which keeps the nucleus together. And since this is what enables us to be here today, that's a really good thing. Okay, so the question is if you want to look inside the proton, or you want to understand the strong force, you quickly run into a problem. It's this very rich environment, but it doesn't leave its environment. It's very isolated. Quarks and gluons always come in bound states. This is a fundamental property of the strong force called confinement. And this is why you can live your life basically never thinking about the strong force. And this is why if you want to study the strong force, it's extraordinarily difficult, because all of the details, these rich details, are really locked inside these very, very small scales. So we're going to make a plasma, so a soup essentially, of quarks and gluons. This is what I want to do, and I've just told you how hard it is, so you should respect that this is a difficult field. So what I want to do is I want to essentially melt these protons and neutrons. So if I want to melt ice, I put it on the stove and it heats up, and then I don't have ice anymore. So what I want to do is I want to do the same thing with the nucleus. I just want to add energy to it so it heats up, so these protons and neutrons melt, and I can get something where the quarks and gluons are no longer subject to confinement. But the problem is that I need to get to a temperature scale that is so hot that it's hotter than anything else. So I can't just put it on the stove or heat it up in an oven somewhere. I need an energy source. So what do? We take 2 nuclei and we smash them together. And then there's all this kinetic energy from the fact that we get these nuclei moving pretty much the speed of light, more than 99.99, some large number of nines, % the speed of light. So as fast as we can possibly get them, and then we run them into each other. And all this kinetic energy serves as the way to heat this up and give us this quark-gluon plasma. So that's experimentally how we're going to do this. And it's not so simple. There's 2 places on Earth where you can do it. One of them is at CERN, as you probably imagined. The other place is at the Relativistic Heavy Ion Collider, which is on Long Island in New York. And so these are the 2 facilities that have the gigantic accelerators that are necessary to get the nuclei to these high speeds such that you can make the quark-gluon plasma. Okay, so what are we going to do? We're going to take 2 nuclei, we're going to collide them together, and we're going to make something. We're going to make this quark-gluon plasma. This thing is going to last for a billionth of a trillionth of a second. That's the time scale. So every time we make this quark-gluon plasma collision between two nuclei, it's over before you know it happened. And it's 1 billion times smaller than the pixel on your iPhone display. So it's like 10 to the minus 14 meters across. And it's 3 trillion degrees. So I guess it's good that it's small and it doesn't last very long because it's really hot and it would be dangerous. But as an experimentalist trying to study this, this is a challenge. So how are we going to do this? Well, first of all, we need something to detect what comes out of these collisions. And for that, we have ATLAS. There's other detectors at the LHC. There's detectors at RHIC. ATLAS was designed, of course, to measure physics beyond the standard model, the Higgs, the other things that you can hear about in these other YouTube talks that they put together. But it actually turns out to be a spectacular device for measuring collisions between large nuclei as well. So the operative point here is that ATLAS is huge. It's 44 meters across, 25 meters tall. These are for scale. You can see people here. It's fantastically large. What are we going to actually measure with this great detector that we have? Well, in each one of these collisions, we're going to collide lead nuclei together because those are big and easy for the accelerator to accelerate, or straightforward at least. I wouldn't say it's easy. It's a technical feat in its own right. In each of these collisions, we're going to make thousands of new particles. We're going to take all that energy that we brought together in the collision, and using E equals mc squared, which you've probably heard of, we're going to make a bunch of new particles. And these particles, which are the remnant of the quark-gluon plasma, the remnants, these provide the only window into the earlier stages of the collision. Because this quark-gluon plasma lasts such a short amount of time, we can't study it in real time. We have to look at the debris that comes out and then try to infer what happened at these very earlier times. So I said we're going to collide 2 nuclei together. And we don't do this once. We do this billions of times. And we look at each collision individually. We look at the patterns inside each collision using a lot of computing, which is also a great technical feat. Okay, so this is what we're going to do. We're going to measure a lot of particles. We're going to use ATLAS. This is what one collision looks like. This is one that was taken, I think, in 2015. You can see at the bottom it has a run and an event number. And what are all these orange lines that are filling up the screen? Each one of these is a charged particle. So pions or kaons for those of you who know. But these are particles and they're bending in a magnetic field of the ATLAS detector, and we reconstruct it using our software. So what I'm going to try to do is I'm going to try to look for patterns in all of these orange tracks in billions of collisions. All right, so this sounds like a great task for someone with a lot of time on their hands. So the first thing I want to do is I want to talk about how we're going to make sense out of this. So, and what we're going to do, since we're talking about these large nuclei here, is we're going to talk about geometry. And I want you to just imagine that these nuclei are very small. On their own scales, there's structure. So you can think of these lead nuclei as like spheres. And we're going to run 2 lead nuclei into each other. And so if I run 2 bowling balls into each other, or beach balls, or whatever you want, there's a geometry according to whether or not they hit right on, or whether they barely hit each other, some sort of glancing collision, or somewhere in between. So I want you to look at these pictures. So there's 2 nuclei here. These are just simulations. One is one is blue, and one is red. So one's going into the screen and one's coming out at you, okay? And the darker ones, the ones that are really the darker circles, are the protons or neutrons from that nucleus that hit something from the other nucleus. The ones that are shaded that you can barely tell if they are red or blue, those are the ones that miss. So the nucleus is a collection of protons and neutrons. The protons or neutrons that hit something from the other nucleus, those interact and form the core of our quark-gluon plasma. The other circles, they just keep on going. And we don't see them, and we're not going to talk anything further about them. So like over here in this one on the left, like these will just keep on going straight, and eventually they'll realize they've lost most of their nucleus and they will break up. But this is where the quark-gluon plasma is formed. in this sort of American football shaped region, or this one, which is more circular, or this one, which almost kind of looks square. Okay, and the reason these things are not perfectly spherical is because these protons and neutrons, they move around. It's a quantum system, it fluctuates. So what we're going to do is we're going to see if we can relate something about the geometry of these collisions to what we measure in the experiment. So what we do is we define a coordinate system because we're physicists, and that's what you do. You start out defining a coordinate system. And so that's what I have here. And I'm going to just define this angle phi. And I'm going to measure where in angle all the particles are with respect to this horizontal axis here. And if I do that for quite a number of collisions, and I just look at the relative number of particles, I get this. So this is the angle. It's in radians, so these are the ones that come out at 0 degrees. That is along this horizontal axis here. The ones that are around 3 and -3, that's pi, so those are over here. And then the dips are in the vertical direction, okay? That's around pi/2. And so what I find is that I get about 25% more particles coming out in the horizontal plane than the vertical plane. This is not a particularly small effect, 25%, that's something you can, it's pretty real. So I'm going to describe this distribution, the number of particles, as something that's proportional to 1, because that's the, I've just normalized this so that it has a value of 1 here in the center, plus a cosine term, okay? And that will describe this peak at 0 and pi, and this depletion at pi/2. And then I'm going to have this quantity V2. This is the amplitude of the modulation. Okay, so you're going to get something that's like about 25% here, as well, times 2. So you're going to get about a 10–15% V2 here. Okay, so I am able to measure something that is sensitive to the geometry, which is a very large modulation of the number of particles. That's interesting. So I get more particles that come out the long side, which is the purple side, that's the horizontal plane, than come out the short side, which is this pink vertical plane. All right, this is interesting. How am I going to understand that? So I want to talk about the difference between a gas and a liquid. Okay, so if I have a gas, something that is low density, let's just pretend that this red oblong shape here is the region of overlap between these two nuclei, like we were talking about on the slide of geometry. If there's not a lot of particles there, no matter which, the black circles are the particles. No matter which direction I go in this case, there's not a lot of particles, I'm not very likely to hit anything. And so I don't know where I am in this red region. If I'm this one here in the center, if I go up, that's fine, I don't hit anything. If I go to the right, I also don't hit anything. If I go this way, I don't hit anything. It's only if I go just a couple of directions, I actually hit something. So I don't know where I am because there's nothing telling me where I am. If I start to add more particles, so more black circles, then it starts to be easy to tell where you are. So I'm just going to add this one to talk about this pink one here. It's pretty clear that if this thing heads off to the right, it's not going to hit anything. If this thing heads off to the left, though, it's definitely going to hit something. And so it's going to be much easier for this particle to go to the right than it is to the left, because it's going to interact, it's going to bounce off of more things. So I could just keep drawing black circles and PowerPoint until the file size was very large. But what I did is I made this. And because at a certain point, it makes sense to stop thinking about particles and to think more about gradients. And if you don't have a great feeling of gradients, think about a hill, right? So here, where there's a lot of particles and there's no good way out in the center, this is where you are at the top of a mountain. Out here, where there is nothing in the white, this is the valley, okay? If you want to go from the top of the mountain to the valley the quickest, it would be just to jump off the mountain. So that's going down the short side. That's a very large gradient. If you want to get down safely, you would go this way, the vertical direction, because that's a nice, safe way down the mountain. Okay, so these particles, what they want to do They are going to go out this way. The steep pressure change is this way. It's the equivalent of jumping off the mountain. The gradual pressure change is in the vertical direction here. And so what happens is that we get more particles in the horizontal plane here because it essentially explodes outwards, because it's so much easier to go out this way. There's a lot more area here where you can just head out in the horizontal plane than in the vertical plane. Okay? I was going to ask you if that makes sense, but I can't see you, so I won't. So this is actually how a liquid behaves. It's not thinking about one interaction like a gas, like the air that you're all breathing right now, but it's thinking about a liquid. And how do we characterize a liquid? Well, you characterize it in some ways by viscosity. So is it a good liquid, like the water, the beach, or is it a high viscosity liquid, like honey, right? You know that if you shake a jar of honey, it takes forever for that last bit of honey to get out. Okay, so that's high viscosity. Water is low viscosity. But I've told you about how we measure V2. V2 is not viscosity at all. But what you can do is if you have a model, so hydrodynamics, which is the fluid motion, that's what hydrodynamics means. So we use hydrodynamic models, our theory colleagues do, to turn V2 into a measure of the viscosity of the quark-gluon plasma. They use a lot of data. This is just showing some from the LHC. And with these models, that is really a very interesting topic on their own right, you can measure what's the viscosity per entropy. That's a measure of the disorder. Don't worry about that. And you can characterize the viscosity of the quark-gluon plasma. And that's what's shown here in this orangish curve. And you can see this viscosity is very small. It's much smaller than water. It's much smaller than helium. So the quark-gluon plasma is an extraordinarily good liquid. That's what we have learned. So that's pretty interesting, I think. But the more interesting question is why? I've told you about the strong force and how it confines quarks and gluons inside a proton, and it's responsible for the mass of nucleus. But there's nothing in what I have told you that would ever lead you to understand why the strong force at very, very high temperatures should behave as a liquid. And that's an interesting question. And to do that, you really have to have some way of looking under the hood. You need a microscope to study the interactions between the quarks and the gluons that ultimately are giving rise to this liquid-like behavior in the quark-gluon plasma. So this is what I would like to do. I'd like to get the quark-gluon plasma, I'd like to put it in a box, I'd like to shoot something into it and measure what comes out. And this is what you do with a lot of conventional materials. So maybe you've heard of X-ray scattering or things like that. If you want to understand what goes on, you take some sort of projectile, you scatter it off of whatever you're trying to study. Now, the problem is that what we're trying to study here doesn't exist long enough for you to take it into a lab and scatter something off of it. So that's really the fundamental problem. However, there's a solution. You knew there had to be a solution because what else would I do for the rest of the talk? So a proton is basically a bunch of quarks and gluons. So if I have two protons running towards each other, eventually some of those quarks and gluons will hit each other and scatter. So these are the blue circles are each protons, they're coming in, and you can tell that they're going to hit each other. And what I'm looking for is actually evidence that a quark or a gluon from one proton hits directly a quark or a gluon from another proton. And if that happens, then they can scatter actually just like billiard balls. So that's what the red lines illustrate here. So some quark or gluon from one proton and some quark or gluon from another proton scattering with a large angle here. Now, a quark or a gluon doesn't get to live very far on its own because of confinement. So that kicks in, and it actually turns this quark or gluon into a bunch of particles. That's what's illustrated by the black arrows, a bunch of the particles of just normal particle physics. But they carry the momentum and the energy of the scattered quark or gluon. That's what you get. Okay, so this is schematic. Why should you believe this happens? The answer is because we've measured it. We've measured it in a lot of places. This is a beautiful event display from ATLAS. So you can see shadowed out a lot of the ATLAS detector. And so what you have is from the left and the right at sort of an angle, these two protons would have come in. This isn't a real proton-proton collision from 2017. They hit in the middle here where these orange tracks are. And then what these yellow sprays are that you see coming out with the green, those are the energy that we measure in the ATLAS calorimeter system. It's a huge amount of energy coming out toward the upper left and the lower right. And if you look over here at this inset, that's the same view I was showing you earlier, one proton coming in and one proton coming out. And you can see that the dominating feature of this event is this huge back-to-back sprays of energy that we measure in the calorimeter here and here. So this is a real example of a jet measured in ATLAS. Okay. Well, protons and neutrons are constituents of these lead nuclei that we're going to make the quark-gluon plasma with. So if I take those protons that I was telling you about on the previous slide, and they're already in these lead nuclei, and I smash them together, this same process should happen, right? So the jets created in these lead nuclei, what do? Well, they have to go through the quark-gluon plasma. And this is our microscope, these very high energy quarks and gluons that are created when quark and gluon from the incoming nuclei hits something from the other incoming nuclei and then has to go out through the quark-gluon plasma. This could be our microscope. And actually, this is a really old event display, but it never gets old for me. It's actually from over 10 years ago now, from the initial running of the ATLAS. Back in run 1. And what you see here in this red circle is the same sort of view that I was showing you previously with the proton-proton collision, only now we're looking at a lead-lead collision. So I've got one nucleus going in, one nucleus coming out at me. And you see these sprays in the calorimeter with these red and green bars now that are very collimated. This is one jet. Now on the other side, instead of seeing a jet, what do I see? I see a very diffuse spray in the calorimeter. If you look at this histogram, which is essentially if I take the calorimeter and I cut it and I just unroll it so you can see it. So this red, this is one jet. On the other side here, I don't see a collimated jet. I see something that is pretty flat. And these are really, these were impressive when you know that what we see in proton-proton collisions. So showing you event displays is cool, but it's not really scientific in the sense that, we want to make plots and make sure we're not looking at just really weird outlier events. So this is a plot that's made by actually my postdoc, Tim. So this is the momentum of jet 2 divided by the momentum of jet 1. Jet 2 is defined as having a momentum less than jet 1. So this ratio can only be less than 1. And these are, the points are in proton-proton collisions. And so what you see is that you're most likely to have something where the momentum of jet 2 is pretty much the same as jet 1. This is what you see in proton-proton collisions. These jets are balanced. That's what we saw in looking at this event display. In lead-lead collisions, we actually see something that's very different. See, we again keep the proton-proton collisions. It's the same axis here, the momentum of jet 2 divided by the momentum of jet 1. And we've now classified these lead-lead collisions in terms of their geometry. So the purple points are the smallest quark-gluon plasma, where the nuclei barely hit each other. The red points are the biggest quark-gluon plasma, where the nuclei smash into each other head-on. But what you can see is in these red points, it's no longer that the most likely value is that the two jets are really well balanced. There's this huge excess of very imbalanced jets, which is exactly what we saw in the event display that I showed you a couple of slides ago. So as I increase the size of the quark-gluon plasma, I essentially increase the amount of imbalanced jets. Okay, so this is good. We've got something. Now let's get a schematic picture. So this is the same event I showed you before, now with slightly different colors in lead-lead collisions. This is an actual lead-lead collision in ATLAS. We've got the one jet over here. We've got the not a jet over here. What's our picture? Well, our picture is that this quark and gluon found each other to create at least the one jet and what would have been the second jet somewhere near the edge. And so this one jet that we see over here that's going up, that one, it had a pretty easy life. It went through the quark-gluon plasma, which is what I'm showing here just schematically as a circle. It didn't go through very much of it. It just made it out. It happened to go out in the direction that was easy to get out. This other one, it had to go right through the center of it. It had a tough life, and it's scattering off of whatever those constituents are in the quark-gluon plasma. So maybe it gets knocked around a bit. Maybe it emits particles, loses energy. The energy has to go somewhere. Maybe it gets absorbed into the plasma. This jet that had this rough life going through the center of the quark-gluon plasma, this is the one that's going to tell us about the details of all these interactions between the quark and gluon, because it experienced all of them. It went through the school of hard knocks, essentially. And so it comes out the other side a little bit worse for the wear, but this is our microscope. So the question we still want to answer is, why does the strong force at high temperature behave as a liquid? But now we have a microscope that we're able to work toward answering that question with these jets. So how do we take a closer look at this? What do we do? I wish I could tell you exactly what kind of quark or what kind of interactions they have, and we don't have a full picture of that yet. We know that they do get knocked around. We do know that one thing that happens that causes these imbalanced jets over here is that they actually radiate gluons. So there are gluons that come out that are really sensitive to the interactions between this quark or gluon and the plasma itself. And so that is thought to be the primary mechanism by which jets are quenched, is this radiation. And what that does is it heats up the plasma. And so we actually are able to look closer to see how that radiation essentially makes a local hotspot in the plasma. That's another talk. It's tough to see. So we have jets as our microscope. So how do we look closer at this? How do we effectively exploit our microscope? So one thing we do, and my group has actually done a lot of this, is to measure the particles around the jet, because if it gets heated up, this is where you'll see it. You'll see it in the particles around it. Another great thing that we do is we measure jets and their correlations with photons and Z bosons. So if you don't know what those are, don't worry about it. But what they are, the important point, is that they go through the quark-gluon plasma and they don't even see it. Okay, they don't interact via the strong force. The quark-gluon plasma is a huge bath of things that interact by the strong force, but they just blithely go through it and they don't interact with it at all. So what that does is it gives us a great tool, because we know how much energy a jet would have had when it started, because it's balanced by this photon or this Z boson. And this is a nice event display of one of those events. The red lines are the muons from a Z boson decay. And then on the opposite side, you can see a jet. And this jet has lost energy, but this Z boson did not. The other thing that we can do, that's another great talk, is we can change the type of jet that we're looking at. So all these jets start from a quark or a gluon. But there's different kinds of quarks. There's actually 6 different kinds of quarks, which I didn't tell you about. And there's also gluons, and they should all interact with the plasma a little bit differently. And so being able to have enough jets where you can really sort this out by the different types of quarks, or whether they started with a gluon, that's another incredibly interesting thing to study. So these are the kinds of things that me and my collaborators within Atlas and my colleagues within the LHC experiments and at RHIC are working toward, and these are really the primary advantages that are going to come over the next, say, 10 years of running at the LHC, with Run 3 and Run 4 at the LHC, is that you need to do more differential studies, you need more collisions. sort these jets into these very different piles, essentially. So this is what I'm looking forward to over the next several years at ATLAS. So another thing you can do, we have this microscope, and I've talked about, looking more differentially at the microscope, but you can also change what you're looking at. And so that's a whole new avenue of exploration that I think is great. So one thing is there's discussion at the LHC right now about running oxygen collisions. So oxygen is much smaller than lead. So if you take these oxygen collisions and you smash them into, or these oxygen atoms or nuclei, smash them into each other, you're going to create a smaller QGP. And so that will enable the jet to be scattered around much, much less. Well, that would be very interesting. And so I'm particularly excited about that. The other thing you can do is you can make a colder QGP. So instead of the one at the LHC, which is very hot, you can make one that's a little bit colder. And that's what RHIC on Long Island is able to do. It's got a much lower energy of the collision, so the nuclei are going slower. And there's a new experiment there that I also work on that's under construction called PHENIX, which will be able to make these same kinds of jet measurements at RHIC. So that's also particularly exciting. So I would stay tuned both for more running at the LHC, potentially new collision systems, and more data from RHIC in order to really understand what's going on under the hood of the quark-gluon plasma. So thanks a lot.
Then thank you very much. And now we can go to the question and answer session. We already got quite a few questions on YouTube. We also collected throughout the day questions on Instagram, for example. So we'll mix them up a little bit now.
Okay.
And hopefully maybe we can stop the sharing so that we can see you. Beautiful.
I think I can.
All right.
Yes.
All right, then our first question that we want to start off with is this state of matter, so the quark-gluon plasma that you talked about, present in other parts of the universe, different from the LHC? And if so, where?
So that's a really great question, and the answer is we don't know. So we know that the universe looked like this about 1/1000th of a second after the Big Bang, when it was really, really small and really, really dense. So that's pretty clear. However, a state of matter like this could exist in the core of neutron stars. And that's not known yet. And there's a lot of really interesting work that's going on in that direction to try to understand how matter made up of quarks and gluons and protons and neutrons exists under very high pressure, because that's what's in the core of neutron stars. Neutron stars are essentially stars that are so dense that they don't exist, they don't have atoms or nuclei anymore. They're just a giant ball of neutrons. And actually, we're getting a lot of impressive new data that's sensitive to this from LIGO, which studies gravitational waves. And I expect over the next several years, we'll know a lot more about the answer to that question.
All right. Then there is another question that is, if the quark-gluon plasma is so hot, and you talked about the temperatures at the beginning, why are the elements and matter that we interact with so normal in temperature?
So what happens is the protons and neutrons themselves in normal matter are quite cold. They exist in just a bound state. That's the ground state. That's, what's a ground state? You can think about just putting a ball bearing in a bowl, right? It's going to go to the bottom of the bowl. That's its ground state. That's where it wants to be. That's its lowest energy state. And most of the nuclei that you're dealing with around you today, oxygen and carbon and things that are relevant for your life, that's in its ground state. It's only when you really, really heat it up that you have to worry, or that you create this kind of matter. And that's good, because we wouldn't exist if you didn't have chemistry as we know it.
Actually stay with temperature a little bit. How do we even measure something that hot is another question. And is it based on measuring kinetic energy, or how does it work?
So this is a really great question. And the answer is you measure the photons that are coming off of it. Just like when they hold that little thermometer up to your forehead so that you can go into whatever you're trying to go into these days, and make sure you don't have a fever. We measure the photons that are emitted from the quark-gluon plasma, because the spectrum of the photons is sensitive to the temperature. It's called black body radiation. And we have been able to measure the photons. And actually, if you look at the Guinness Book of World Records, the highest temperature ever recorded is attributed to the ELISE experiment at the LHC, and it comes from measuring these photons. So that's a whole nother talk, and it's very interesting.
Very nice. All right, then we get a little bit more specific. Can the quark-gluon plasma help in understanding solar neutrinos?
So that's a good question, and I think the answer is no. So the solar neutrinos, they come from the sun the sun is basically a fusion reactor. And so the neutrinos come from the details of that fusion, those fusion reactions that exist in the sun. And as I was talking about on the very first slide, that's actually, it's 15 million degrees Celsius. That's quite a bit colder than the quark-gluon plasma, which is, a few trillion degrees.
And there's an add-on question to that. If it's not exactly connected to that, but how can the quark-gluon plasma help us to understand maybe other phenomena? Where do we learn something? Where can we apply what we learn from the quark-gluon plasma?
So that's a really great question. And the first answer is that this is basic research, and understanding the strong force is very important, because nature has only given us, as far as we know, 4 fundamental forces. So understanding one of them in this very unique realm is important as basic research. I think that goes with the connection to neutron stars and trying to understand things that are further away than our solar system or our galaxy or something like that. There's another connection, is that this isn't the only. This is a very good liquid, but there are other systems that behave as very good liquids that you can also understand along with the quark-gluon plasma. One of those is ultra cold atoms. So if you take atoms, you put them in a trap, and you cool them down to very, very low temperatures, and then release the trap, you see behavior which is very similar to the explosion outward that I was showing you with the quark-gluon plasma. So there's some interesting connections there into other systems where the interactions are really, really strong.
All right, and then going a little bit of a different direction, you mentioned that we collide lead nuclei, and we also are thinking about colliding, for example, oxygen, you mentioned at the end. So there's a question of, is there a chance to have a quark-gluon plasma, and now we're really going low, in an electron-nuclei collision?
So that's a great question, and the answer is yes. So Atlas just put out the first paper on this, and when I first saw the results inside of Atlas, it surprised me. And it turns out that, but it's not an electron, it's a photon. And it turns out that you can think of a photon as a photon is a primary particle, but it can fluctuate into something that looks like a quark-antiquark pair, and it can act as essentially a strong force projectile onto a nucleus. And it turns out we did see it there. We did see something that looked consistent with the quark-gluon plasma formation, these same asymmetries in the particle production in photon nucleus collisions. People have looked in electron-positron collisions and have not seen evidence for some sort of quark-gluon plasma formation, but there is it's another great talk. There is evidence that a very, very small quark-gluon plasma might be formed in proton-proton collisions or proton nucleus collisions. And so there's a lot of really interesting things to study there in the very small size limit, even smaller than oxygen.
did we actually in the LHC collide other things than lead on lead?
Yeah, so the LHC has a lot of data on proton-lead collisions. And that's very fascinating. And at RHIC, they've done proton-lead, deuteron-lead, so that's the bound state of a proton and a neutron, and then helium-3, which is 2 protons and 1 neutron, gold collisions. So they're really able to change the shape of the projectile. And those results are very interesting. It really looks like we create a quark-gluon plasma even in these very small collision systems compared to lead or any other big nucleus. What's interesting that we haven't seen is we've seen these particle asymmetries suggesting this explosion outwards, like I was talking about in the first part of the talk, but we haven't seen the modifications to jets. And in my mind, and I think the mind of a lot of members of the community, that's a urgent question to get better answers on.
Then, yeah, I think we go with this one. There is the question, what is the, is there any similarities between the normal plasma, which I guess refers to in the industry application, sort of electromagnetic plasma, and the quark-gluon plasma that you focused on?
So the reason this is, what characterizes an electromagnetic plasma is having free charge carriers. So you think about an electromagnetic plasma, that's what it is that there's electric charge carriers that are free to move around. And here we have charge carriers of the strong force that are free to move around. And what I think characterizes all of this is the very strong interactions between the constituents. The plasma you think about in plasma physics is, of course, at a much lower temperature than what we were looking at here at the LHC.
Then we have a bit more detailed one, which, yeah, which is, if you could explain a little bit more the hydrodynamic model that converts this variable V2 that you talked about into, or relates it to the viscosity that you also talked about.
So what this is so hydrodynamics, first of all, I'm not a theorist, so people down the hall could answer this question in a lot more detail than I could. But what you do is you take some equation of state, which is a relationship between how this thing responds, the quark-gluon plasma, and then a hydrodynamic model just describes how it evolves. You conserve energy, you conserve momentum, and you watch these little, you use a lot of computer simulations to watch these little fluid cells as they move around. And then at the end of these simulations, you convert these into particles, the particles that we measure, things like pions and kaons and such. So what these models do is they run these kinds of calculations, and then they use actually a Bayesian analysis to ask what V2 value, what is the most likely viscosities for the V2 values that we measure? And so that's essentially how these calculations work. So it's really running it backwards rather than forward, saying, here's a V2, what's the viscosity that comes from that? It's, if I had these conditions, what V2 would I have gotten?
And then there's another good one, interesting one. Is there a relationship between dark matter particles or gravitons and the quark-gluon plasma?
So I think the answer there safely is not, as far as I know. But since nobody knows what dark matter is, and nobody's seen a graviton, I guess I can't rule it out. So what this is really the strong force. And people know dark matter is there because we've seen evidence for it in space. So that's a lot of gravity. And gravity doesn't really play a role in the quark-gluon plasma. Okay.
All right, then another more detailed question. How can we increase the timescale of a quark-gluon plasma and explore more parts of the QCD phase diagram? Maybe we can touch on that a little bit first.
Okay, so the QCD phase diagram is essentially, think about a plot that has temperature and density. So what we are here at the LHC is we're at a very high temperature, okay? And neutron stars are much colder, but if they were to have a quark-gluon plasma in them, they're at a much higher density. So those are really two ends of the spectrum. And so the question is, experimentally, are there places where you can go where you're at a more moderate temperature and a more moderate density? And the answer is yes. So there are other places where they are colliding large nuclei at lower energies. So one of those is RHIC. Actually, the RHIC run, right, that's ongoing or finishing up right now, is actually not targeted toward jets or that. It's actually running it at the lowest energy you can possibly operate this collider to make a much, much colder version of the quark-gluon plasma. You wouldn't make very many jets in that, but it's going to be something that is colder and potentially has a higher density because these things don't blow through each other quite so fast. And so that is work that's ongoing. There's also the HADES experiment in Germany that's also doing that at an even lower energy. And so that is a way to essentially map out parts of the phase diagram between the LHC, which is the highest energy collider, and say, neutron stars, or very high density, colder matter. Okay.
All right, then I think we can close it up. Maybe there's maybe a last one that showed up several times. If there's any recommended books or literature or sort of reading material that you can recommend for those that are further interested in quark-gluon plasma and heavy ion physics.
So that's a great question, and the answer is that there's not a lot of books that I'm aware of. There's some Atlas physics briefings, which you can find in the information for this YouTube channel that are very relevant. And I would say that the best thing you can do is to Google around. I know Atlas and CMS and ELISE, which is a targeted heavy ion experiment, and LHCb. There's a lot of great stuff. If you start to Google around about the quark-gluon plasma, you can find a lot of interesting stuff just on the internet. And starting with these Atlas physics briefings, we'll talk about jets like I've been discussing here, but there's a whole lot more detail. And so I would recommend that as a good starting place.
All right, recommending Atlas briefings is always a good idea. Everyone should read them. All right, then I think, thank you very much for this very interesting talk, and also for addressing all the questions that we got on YouTube and on our social media channels. And so thanks a lot again, Anne.
Well, thank you.
Thanks a lot also to everyone out there that joined today's talk. Thanks a lot for all the questions. We hope to see you again soon for our next upcoming talk. Stay tuned, look at our social media channels and the YouTube channel to find out when and where that exactly will be. And then we hope to see you again. So thanks a lot again, Anne. And that's it from our side. So goodbye.
Thanks, everyone.